To transition from the low-level mechanics of running processes to high-level operating system policies, we must explore how a scheduler decides which job to run. To build a foundational framework, we begin with 5 highly simplifying workload assumptions. Every job runs for the exact same duration. All jobs arrive in the system simultaneously. Once started, each job runs to completion without interruption. Jobs perform no input-output operations, and the exact runtime of every job is known in advance. While mostly unrealistic, these assumptions allow us to compare basic scheduling policies using our initial performance metric, turnaround time, defined as the completion time of a job minus its arrival time. The most fundamental scheduling policy we can implement is first in, first out, also known as first come, first served. Under our strict initial assumptions, where 3 jobs A, B, and C arrive simultaneously and each run for 10 seconds, first in, first out performs reasonably well, yielding an average turnaround time of 20 seconds. However, the moment we relax our first assumption and allow jobs of different lengths to run, first in, first out suffers severely. If job A requires 100 seconds while B and C only require 10 seconds each, B and C are forced to win a queue for a massive 100-second window, driving the average turnaround time up to a painful 110 seconds. This performance bottleneck is known as the convoy effect, where a series of short consumer requests get queued behind a single heavyweight resource consumer, much like getting stuck behind a packed grocery cart when you only want to buy a single item. To resolve this, we can borrow a simple optimization principle from operations research: shortest job first. By running the shortest tasks, B and C, prior to the lengthy job A, we dramatically optimize the schedule. Under shortest job first, the average turnaround time is slashed from 110 seconds to just 50 seconds, representing a massive performance improvement simply by altering execution order. While shortest job first is provably optimal, when all jobs arrive at the exact same moment, it struggles when we relax our second assumption and allow jobs to arrive at arbitrary times. If job A arrives at time 0 and starts its 100-second run, and the 10-second jobs B and C arrive just moments later at 10, a non-preemptive shortest job first scheduler is powerless to intervene. It must run the active job A to completion, forcing B and C to wait and triggering the exact same convoy problem. To solve this limitation and accommodate dynamic arrival times, our scheduler requires a more aggressive mechanism: the ability to actively stop and resume processes.